Hi everybody and welcome back. This is Craig Robertson with UNM IEEE, and I was going to go over some basic logic gates. So the first one I was going to go over was the OR gate, and the OR gate is a pretty simple gate. It's you draw it just like that. It's classified by the curved back and kind of the pointy nose, and what the OR gate is really used for is you can kind of, if your inputs here are X and Y, and then we'll call the output out just to make it simple. Then if we set up a basic truth table 0 0 1 1 0 1 0 1, so this will cover any kind of scenario that we might run into with our OR gate. Now an OR gate means that either X is 1 or Y is 1. So for our first case here, X is 0 and Y is 0, the OR gate will stay a 0. Now if X is 0 and Y is 1, it's getting a 1 from Y, so it means either X is a 0 or Y is a 0, hence the OR Y is a 0. So that means that it will return a 1 right there. So there we go, that's a 1 out. Now, in this case, we have X is 1 and Y is 0, so either X is 1 or Y is 0. This will return a 1, right? Because one of the two inputs was a 1. That's the basic rule of thumb with the OR gates, is if one of the inputs is a 1, it will give you a 1 out. Now in this case, both of them are a 1, so it gives a 1 out. All we need is 1 for them to be 1, but if they're both 1, that's okay. However, if both are 0, it will return a 0. So that's our first logic gate, is an OR gate. And it can have as many inputs as you need it to. Now, like that would be a 4-input OR gate. It only has one output though. Now the complement of the OR gate is what we call the NOR gate. And for a NOR gate, we just put a little bubble on the front. They can have as many inputs as well and out. The NOR gate, which is short for not OR gate, it has the complete opposite truth table. So if we add another column onto this, then we could call it, NOR, which allows us to, all it is it's the knotted output of the OR gate. So when you knot an output, then you just change all the zeros to ones and the ones to zeros. So for the NOR gate here, we can go 1 0 0 0. So that's our basic truth table for the OR gate and the NOR gate. Now let's try the AND gate. I'll go ahead and separate that so we don't get too confused here. So the AND gate here, the AND gate's a pretty simple gate as well. Everything can be pretty much taken down to ORs and ANDs. Well, really, NORs and NANDs are the basic gates that everything can really be broken down to. You'll get into that a little bit later in the semester, but first let's focus on these basic gates. So this would be the AND gate. The AND gate is characterized by the flat back and kind of the curved nose, where the OR gate has kind of a pointed nose and a curved back. AND gates have a flat back and kind of a curved nose on them. And this is just when you're drawing them out in the schematic. It's kind of just a shorthand for engineers. So the truth table for our AND gate, and I'll make a note that this is the OR out. This will be the AND out here. And then we can do a truth table for it. So I'll set it up exactly the same way that we did for our OR gate. And so that way we cover any possible combination of these two, right? And so an AND gate is characterized by, it means that, so X and Y have to be 1. And as we can see just from this truth table here, if we look at every single case, then we can say, okay, if we want x and y to be 1, then there's really only one scenario when that happens, right? So that'll return a 1 if both x and y are 1. The rest of the times, they're not both 1, so we can just go ahead and fill in zeros there. Now, the complement of the AND gate is the NAND gate. And you guessed it, it just has a little circle on the front of it. It's an AND gate, but it's a little circle on the front, and that's a NAND gate. So we'll go ahead and make the truth table for the NAND gate too. And NAND gate stands for not AND gate. So, all we have to do is we say, alright, well, what's the complete opposite of an AND gate? Just flip all the bits, and that's our truth table for the NAND gate. So, let's go to our last one. It's a little bit of a tricky one. And let's go ahead and go over the XOR gate. Now, it's called XOR because it is really the exclusive OR gate is what it's called. We kind of shorthand it, so it's exclusive OR gate XOR. So, let's go ahead and make a truth table for this one too. And then we'll do XOR right there. So we'll go ahead and do the same truth table. We'll make our rows so we don't get confused for what equals what. And let's take a close look at what this actually is. It's exclusive OR gate. It means that it's exclusively an OR. So what we're trying to do here is we're trying to kind of make it just a little bit more exclusive than the OR gate, because the OR includes the 1, 1. And what we want to do here is we don't want to include that 1, 1. So this is a special gate that gives us a 0 when they're both 0. And then a 1 when either one of the inputs is 1 and the other is 0. But when they're both 1, it will give us a 0 as well. So really you can kind of look at the usefulness of this is it's kind of a difference checker. It'll return a little flag when one thing isn't like the other. So it returns a flag when there's an issue with the output. Oh, and I forgot to draw it for you. The XOR gate looks just like an OR gate, but it has another little curve back there. And it can have as many inputs as you need it to. It only has one output, just like the OR gate. But the big thing to look for an XOR gate is it has that extra little curve back there, and that'll let you know that it's an exclusive OR. Now, the converse of an exclusive OR gate, or an XOR gate, is an XNOR gate. That's right, XNOR, so XNOR. So, we can all guess what the symbol for an XNOR gate is. Right? Just a little bubble right there. And that'll make it just a little bit easier to determine what's an XOR, what's an XNOR. Always look for the bubble. That's the knotted gate, right? So it's always going to have the N in it. Now the XNOR, that gate has exactly the opposite truth table as the XOR. So just like that, right? So we can see the usefulness for this gate is it will return a 1 whenever one input is exactly like the other. So if we're looking for a parity checker or some kind of function along those lines, then an XNOR is actually the gate that we really want to use. So keep that in mind when you're building your circuits. All these circuits, they work together, they stack up. You can use them in sort of a sum of products form, which would be kind of shown like that. So as you can see, you can kind of stack them and make much more complex circuits out of them, and this is just the beginning of digital logic. You're on your way to a wonderful semester if you start to understand these. Cool, well that's my time for today. Thank you guys for watching, and if you ever need any help, come and see us at room 312 in Innovation Plaza. We are IEEE, and happy studying. Good luck, guys.